Sum of two first. Sorry, that wasn't a product. That was a sum of two first-order systems. Both of these look like this. They're both soggy response, and that's heavily damped. The poles are all real in the transfer function. As the gentleman said, if we now free up, or we allow our system to have complex poles, let's take a system like this. The other one we had, first of all. Then that's got complex poles, because we've got s squared plus s plus 10 as the transfer function. Or what have we got? We've got s equals minus b minus 1 plus or minus 1 squared minus 4ac, which is 40, equals 2. So s is equal to minus a half plus or minus root 39 over 2. So we've got minus j39 because that's the square root of the complex number. So here we now have complex poles. We've got a real part of minus a half. What's root 39? It's 6 and a bit, isn't it? 6 and a half, something like this. So this is about 3.2-ish of order. So the imaginary part is about 3. J 3.2 and minus J 3.2. The real part is minus a half. So the poles go here and here. These are complex conjugate. And the reason they're complex conjugates is because this system came from a real differential equation with real coefficients. When we get our polynomial, this thing, its roots have to be real, or the net effect of them, the imaginary parts have to cancel to get real coefficients in this differential equation. So the complex conjugate bits are necessary for the imaginary parts to cancel. So there's our lightly damped system. There's a special case called critical, where the two poles sit on top of each other in a second order system. That's when it just doesn't oscillate. So the general behaviour of a second order system is the poles start far apart, that's heavily damped. They move together as the damping reduces, and they sit on top of each other, which is critically damped. Then they move off the axis, which is lightly damped. So it's called the pole locus as you reduce the damping. You reduce the amount of this stuff, the damping term. Okay, now all of these have negative real parts. If we have a system like this, then clearly you're going to get a pair of complex conjugate poles on the other side. This term becomes positive, and the whole thing blows up. The time domain solutions grow exponentially. So that is called unstable. It doesn't matter whether they're real, or whether they're on the real axis, or whether they're on the imaginary axis. The real part will go positive, and the whole thing will blow up and become unstable. So this part of the thing is unstable. That's what we call pole stability. I mean, if you want, you can work it out why this happens. Let's take our first order system that's nice and stable, because you can work out what its impulse response is. If you remember, the impulse response h of t, let's have Elsa again. Okay, stamp. This is a magical impulse response. It's not a real or complex one, it's magical, but she stamps hard. She kicks the system and something happens. So the system is kicked with an impulse and we get something at the end of it. Well, the impulse response h of t is the inverse Laplace transform of the transfer function. It's easy to see why. In general, y of s is h of s. U of s, well, An impulse, delta t, according to your sheets, has a Laplace transform of 1. So a kick, an impulsive stimulus, means that u is 1. So clearly, the Laplace transform of the output to the system given a unit kick, an impulse, is just its transfer function. So the impulse response is that, it's the inverse Laplace transform. So there's h of s, so for our first order system s plus 1. If you look up its inverse transform, you get e to the minus t. Okay? Which just decays soggily. If in contrast we had the system dy dt minus y equals u, then we'd have had a transfer function s minus 1. That would have been plus t, and it would have been blown up. And the same happens for lightly damped or heavily damped second order systems that are unstable. So this is about stability. And you can see its effects in either the Laplace domain or in the time domain. Okay, so there's one more issue to do with stability, and that's called bounded input, bounded output stability. Let us suppose, let's write down our general properties of the system. Right, let's decide that our input u of s is equal to a unit step. In the time domain, it's just u of t that jumps up to 1. So that has the Laplace transform 1 upon s, if you look it up in the tables. So you've got y of s equals h of s 1 upon s. So if we go across like this, there's a general theorem that says if you take the limit as s tends to infinity for both of something, you get the limit as y of t tends to 0. This is in other words, we apply a step to it, and this property of Laplace transforms tells us what happens as soon as the steps arrive. Well, it should be fairly clear that if that looks like 1, the transfer function looks like 1, or it looks like s plus 1, or s squared plus something, or whatever, then if you look up in the table of Laplace transforms, y of t is going to contain impulses, or derivatives of impulses. It's going to contain spikes. So you've got to have it looks like something like s plus 1, sort of s squared plus something, whatever. It's got to have a denominator whose order in s is lower than the numerator. If it isn't, you get, for a step input, a spike output. So a finite input, even though it's a step, gives you an infinite output, and that's called bounded input, bounded output stability. So if the input's bounded, like a step, you want a bounded output. And that's conditioned as the order of the numerator is less than the order of the denominator. So that's the other side of stability. Right. Well, trying to think what else we did in Laplace. What else did we do in Laplace? No, not much else, I don't think. Now, getting on to what's called frequency domain and frequency domain design. Anyway, there were more questions before. Any questions now? Please just stop and interrupt at any time. No? All right. Frequency domain. Typically, large numbers of quantities in life have a time response. Looks like this. Whether it's air fluctuations past an aircraft flying along, bumps in a road, could be the course a ship steers, could be sound waves from a microphone, it could be communication signals, all sorts of things. many of them look sort of generally like a waggly line. And you can make u of t from the sum of sinusoids. In general, an integral, but some will do. So you've got lots of magnitudes and phases and frequency components, and you can generally make it like that. Now, because the system is linear, if I know what it does to one of these, just one, I can then add up the effect of lots of them. That's using linearity. It's basically what linearity sets as the position. So, because so many things in life look like this, it's important to look at the behaviour of systems subject to sinusoids, and also it's useful from a design point of view. Now, there's a very general result. If I have a box with a transfer function h of s, u, t, if I put in time signal u of t, where u of t is something like cos omega t, what I get out is y of t is magnitude of h of j omega times cos omega t plus the phase angle of h of j omega. H of j omega is just take h of s and set s to j omega. And it's called the frequency response function. H of j omega is frequency response function. And what we are interested in is its magnitude and its phase angle. So what it says in general is if I put a sinusoid in here, in the input, I mean, I can make it a bit more general if you want. I could call it b plus phi. Make it a bit more general, shall we? What is it done? I'll put in here b cos omega t plus phi. So what I get out here would be b, and that will be plus phi. Just a bit more general. What happens is the size of the sinusoid, let's say b, is multiplied by the magnitude of the frequency response function, and the phase is shifted by the phase angle of the frequency response function. So that's what it does to an individual sinusoid, and if you want to find out what it does to a lot of them, you just do this. As simple as that. They just apply simple residual. Okay, now I think you ought to do something now, because you're presumably, I would have nodded off half an hour ago. Some of you are beginning to nod off now, understandably. So you should do something. What do you want to do to wake up? If I just go on and on and on, there's a limit to what you can take in. So what do you want to do? You want to write something down? You're desperate to write something? It doesn't have anything to do with this course. You want to send somebody an email? Do you want to ask a question? Heaven forbid. Or do you want to stop at this point? Come on, it's your class, your fees. Within reason, am I doing? Yeah?
What's the degree of damping?
Degree of damping, right. Let's take two extreme cases. Right, that's the second order system. The damping always enters through the first derivative term, right? It's the size of this coefficient, I call it alpha. Now for this one, it's clear that this, if you do the SE stuff, it will have complex poles, won't it? If you had this one, it will have real poles. So in general, I'm right. And you'll see why I'm writing this nonsense. If you write that, this you get, what do you get? You get S equals minus 2 eta omega naught eta plus or minus b squared